Hi everybody, welcome. Thank you so much for braving the impending difficult weather this evening to come and learn about the electrification of domestic hot water and passive house. We're so excited to see so many of you out here tonight. My name is Alexander Gard-Murray. I'm the Executive Director of Passive House, Massachusetts. And I just want to start with a few words about Mass Save, who are making this event possible. Mass Save, as you know, is a coalition of the state's utilities working to make the whole state more energy efficient. And there are really robust passive house incentives, both for single family and, related to the topic of tonight's talk, multifamily buildings. And those start at $3,750 per unit for multifamily buildings before you get into additional adders, which can add even more. And so we recommend that you reach out as soon as possible if you're starting a project. For multifamily, the email is multifhr@icf.com. You can also contact Passive House Training MA at icf.com. And Passive House Massachusetts, as always, is here to help you with your passive house work, and you can go to phmass.org to learn more about us and get help with your passive house work. We've got a bunch of events coming up soon. We've got a tour of Winthrop Center, which you can find more details out about on our website. We've got a tour, we have a talk on a project in Dorchester, an urban infill project that we're really excited about coming for our next monthly meeting. And I also wanted to remind people that the deadline to apply for the Passive House Network Conference is this Friday, the 13th. So lucky time to apply. Tonight's topic is presented by a very august speaker, the president of the Passive House Massachusetts Board and the president and founder of Petersen Engineering, James Petersen, PE. James, let's come up. Let's give James a big round of applause. James, thank you so much.
Thank you, Alexander. All right. Super excited. I just wish I weren't doing this after my bedtime. No, I appreciate everybody coming out. It's supposed to snow a little bit. And this is a very interesting topic to me. And I've gathered all my favorite facts and put them in one presentation. We're going to move pretty fast. There's a need for me to be a little provocative. Hopefully I'm sufficiently provocative and effective in some of my comments. A little history on us. We're an MEP FP firm. We're 18 people. We've done a lot of passive house projects. We're at about 70 large. They're generally multifamily, generally in Massachusetts. So we've been doing this for a long time. And we've been doing a lot of multifamily for a long time. So last count was over 26,000 units of housing since 2008 as an engineer of record. And our first project that got us started in Massachusetts was actually Castle Square, which is a wind project, way back in 2008. It was an occupied rehab, deep energy retrofit. They received federal grant money to make that happen, and that was our introduction into the Massachusetts marketplace. So tonight we're talking all about domestic hot water. I want to talk about options for multifamily. We do want to cover some physics, which I'm excited about. It's fun. We're going to talk about hybrid heat pumps and the problems associated with hybrid heat pumps. We're going to be talking about central plants and also high COP, I like to call them, established technologies for reducing the amount of energy we need to add to water to have a comfortable shower. And that would be solar thermal and heat recovery. Not the kind of heat recovery that includes a compressor, but basically just copper and copper touching, separating the waste stream from the makeup water stream. And then we're going to get into sizing and essentially right sizing or downsizing to only install infrastructure that you need and not more. So oversizing is a problem. So that's what we're going to cover. So it's a little strange that this is provocative, but electricity costs a lot more than gas. And so it's hard to nail this down for a few reasons. One is the units. They're sold in different units. Matter of fact, gas is sold in like 3 different units. And so it's really hard to nail it down. Also, it varies by location. Even in Massachusetts, it varies a lot by location. Some locations have municipal electricity. Municipal, no. Somebody help me out. Is that the right term? It is? Okay, municipal. So they tend to have lower rates historically.
James, I'm sorry to interrupt.
Yeah.
The slide deck isn't showing up online. I'm just gonna.
Okay.
You can keep talking and I'll figure it out.
Okay. So this example, what we do is that each time I make a presentation about energy costs, I go to an actual one of our projects and I take the utility bills from that project and I calculate electricity. It's all in. You know, if the owner uses a certain amount of kWh in a month and their bill is $10,000, that's the all in. So it's the cost for the generation and getting it to your facility. So it's all in, and same with natural gas. The natural gas bills are a little less complicated than the electric bills. So that's another factor that makes it hard to compare energy costs, is the complexity of the bills. And then you may get your electricity generated from one vendor and it delivered by another, and then you have to chase down 2 bills. So it's hard to get accurate building data. And Alexander here was asking if the board could provide data, energy use data for passive house projects. And probably the most complicated, well, there's 2 hard things about that. One is people aren't inclined to share their costs, and then getting the costs right. So whenever we're tasked with understanding someone's utility usage, we want to see the actual invoices. If somebody's put something in a spreadsheet, we haven't seen that as accurate. How are we doing, Alexander and Beth?
Better.
Better?
Yeah, they can see something, yeah.
Okay, all right. Should we do something else for 5 minutes?
No, keep
I
going.
can tell it.
No, you
No?
keep going.
Okay, no jokes. All right. So physics. So water is amazing. So we're going to focus on the things that are amazing about it in relative to heating water for showering. But one of the things amazing about water is the amount of energy it takes to heat it. And that hurts us in this case, because the amount we need to use a tremendous amount of energy to heat it to a known temperature. And the known temperature is about 107, and that's a temperature at which we're comfortable showering. And it's pretty universal. Some of us like a little hotter than others, but it's pretty close, plus or minus, not much. So we have to heat it, and to heat it, we have to add a lot of energy. Just for perspective, air is, to heat a pound of air requires a quarter of the amount of energy as water. So it's hard to compare those 2 as well because the density is so different. So 13 cubic feet of water is about a pound, and 1/8 of a gallon is about a pound. The pound for pound energy required to heat them, 1 degree, is a multiple of 4. And a fun fact is 1 BTU per pound per degree F. Does anybody want to say why that's 1? This is like high school, but that was a long time ago. No one? Okay, so the wise guy, I can't remember his name, I think he was British, he established, he in his little lab, he measured how much heat was required to heat 1 pound, 1 degree. Coming back to you. Do you remember his name? No. Someone could Google it right now. So that established the BTU, the British Thermal Unit. So he was a British guy, obviously. And that's where that comes from. So here's another thing that I prepared for this, is just measuring the amount of energy to heat water compared to air. I just said what that was. And then rock. Okay, so I picked a rock made of marble. Marble requires less energy than air per pound. It's so counterintuitive. And then how about steel? So I picked a metal. Iron, even less energy. So there aren't there aren't too many materials. There's no common substance. It requires more heat to elevate in temperature than water, which works to our disadvantage. The other thing, though, and this is a pro in this context, is that water could be a pretty good battery. So you could heat water with solar thermal when the sun's out. You could store it and then use it for when people are taking showers in the evening or in the morning. So it could work as a battery that way, and it's a low-tech battery, and that's why I like it, low-tech. Turns out it's expensive to store water, unfortunately, counterintuitively. It's expensive, it's heavy, and so if you're storing it, you're going to need structural support, and you're also going to need a pressure vessel, which is expensive and also heavy. So here's another interesting thing that I didn't know until we did a water treatment plant, is how much the water varies around here. So in the winter, when we have ice on the reservoir, it's about 38 degrees. So the low temperature in where this is 30 years of data from the Massachusetts Quabbin Reservoir. It's from Massachusetts Water Resource Authority, MWRA, and they supply most of the water for Eastern Mass. So in New Hampshire, Maine, and Vermont, where it's ice over, the low temp becomes a flat line, because when the ice is over, the water temperature is stable, and it's about 38 degrees. And then in the summer, it also it's raised and surprisingly high. It can be in the high 70s, but we can count on it being in the high 70s in August. So there's a delta of 2 in terms of how much energy we need to add to water in the winter compared to the summer. Factor of 2. Each degree you raise the water requires the same amount of energy. It's proportional. So there's a big difference between winter and summer. So that's something to keep in mind. So now I'm going to shift gears and get into hybrid heat pumps. And I call them local compressor-based water heaters. Because in my career, there's something about the word heat pump that makes people think it's special. It's not special. It's a compressor-based system, which means it's got moving parts and it doesn't last very long, and it's more complicated than desired. So what we're going to focus on is there's 2 problems with hybrid heat pumps in this climate, and more specifically in individual apartments. One is the cold draft they create, and the other is they're extracting heat from a volume that you just heated with another heat pump. And it turns out when you have a heat pump, 2 heat pumps in series, the efficiency tanks. No pun intended, tanks. So problem number 1. So this is the abridged version of this presentation. If you would like all the math, I can give you the unabridged. You just need to contact me at james@petersenengineering.com. So if you heat 20 gallons in the summer, because of that delta T, it's going to be 2 hours of cold draft. So in a small apartment, 2 air changes per hour. So 4 air changes over 2 hours. It's a lot of cold air. Its supply temperature to the space is 55 degrees because it's basically using a conventional refrigerant circuit that's delivering air at the lowest possible temperature, which is similar to HVAC because that's not only the lowest possible temperature to not freeze the coil, it's also the temperature at which the supply then mixes with the air and you control relative humidity in the summer. So it's kind of a coincidence. But it's cold air, and in a hybrid heat pump it's about 200 CFM, which is what they say a dryer moves, but I don't think a dryer moves that much. But think of a dryer and how much air that moves. It's going to move that for 2 hours to heat 20 gallons in the summer. And just really easy math, it's going to be 10 gallons in the winter to run 2 hours because we're having to do twice the amount of work So it's going to be a cold draft for a long time. In the summer, you think, oh, that's great, dehumidified cold air. Well, we need it in air conditioning. Well, you don't need it all the time, and you probably don't need it when your water heater's heating. So it basically ends up a uncontrolled source of air conditioning in the summer. And in the winter, it's a nuisance because you don't need air conditioning at all. But here's the solution. If you don't shower and you don't use your water heater, there's no draft. So if you heat 0 gallons, there's no draft. Slipped in a joke there. How are we doing online?
We're good.
Can we get a question from online just to make sure people are paying attention?
We're watching the chat.
Okay. Okay, so heat pumps in series. So this is the problem. And I did actually, it was at the Passive House Symposium probably 3 years ago. And I said, I think it cuts the efficiency in about by 2. So if you had 2 compressors in series, if you thought you were going to have a 3 and a 3, you're going to end up probably with a 1.5. Because my logic was that you're basically moving the same heat with 2 compressors. So each compressor's operating to move that heat. So it seems like twice as much energy, half the efficiency to do the same work. But since then, because if you were there, you know I was heckled. And so there was some urgency for me to go and put some numbers on that. So I had help from friends and figured out what the actual formula was. But this is basically a diagram of what's going on. Is that on the left you see the work that you're doing 1 unit of electricity in to move 2 units. So you got 1 unit in plus 2 units, 3. That 3 units out over 1 unit in is your COP. And then you're taking that heat, and so now you're 3 units in and 1 unit in, and you're going to get 4.5 out. And so that's diagrammatically what's going on. And here's the formula. And so Doug, who's here, we were really scratching our heads over, we couldn't understand what, at least I couldn't understand what the -1 was for in the denominator. So I asked, it was early days of AI, 2 years ago. It's still bad, AI. So I just asked about compressors in series. And it came up with a formula, and I think it actually had it right, but I didn't know it was right. So I said, what's the -1? I was really wanting to master my understanding of the formula. And it came back with a new formula that dropped the -1. Worked for me. So I've done a little plug and chug for you. And so if you look in the far right, we're talking about 2 compressors in series, the orange and the green line. So if they're both COP of 3, you see that when they're in series, we get a net result of 1.8. So what it means is that your overall system, if you think about the apartment as a system, and we're heating the apartment, and then we're heating the water. If you have 3 and 3, which is really good, your net overall efficiency of that system is 1.8. Nothing to write home about. And if you get a little bit more realistic and you assume, say, 2 and 2, which is the far left, you get an overall system of 1.3. So you've spent a lot of money, you've done a lot of work, and you're only 30% better than electric resistance at that point. So this should be provocative. Is anybody upset or?
Someone online wants to know what's your take if the heat pump water heater is in an unconditioned basement over 700 square feet?
Yeah, so we get a lot of ideas around this topic, and one of them is the basement. So in New England, you have the basement. So the basement is misunderstood as a heat source, but it's not. Let's see, how can I say? So for one, your ground temperature around here is about 50. It goes down as you go north and up as you go south. So you do have an infinite source of 50-degree air, but the heat pump doesn't work at 50. and it doesn't work particularly well at 55 or at 60. So you've got a undesirable condition in that way. What you're better off doing, because we also do HVAC and we understand enclosures and heating and cooling loads, and I've done this for both single-family homes I've ever owned, is you want to bring your basement within the enclosure ideally, because 50 degrees, even though it's a small delta T, 75 or 70 to 50, it's still a delta T. So you're best off bringing that into your enclosure, and now you have basically no free heat. So albeit low quality free heat, if you will, 50 degrees, if you cut it off and you bring that basement into your enclosure, now you have no free heat because you've done a good job on your enclosure. So it's not good. But I'll tell you where it works great. It works great outdoors in a warm, humid climate that's warm and humid year-round. So these are great under like an overhang in southern Florida. Not northern Florida this year, it's been too cold. But you can get reliable operation at a high efficiency when you have a truly infinite source of heat and humidity. You had a question?
Oh, I was just going to say,
Same thing?
yeah. What about though a closet in the center of your? It's mostly closed off here. I mean, there'll be some loss to the ambient space, but it's not.
A closet, so you can't have them in a closet because it needs to extract heat from something. So in an apartment, think of that as a big closet. It's just not enough volume there either. And you're also, pardon me?
You need airflow.
Yeah, you need airflow, right, right. Now, the one real adjutant here is that Mass Saves incentivizes these going into apartments. So incentives should be designed to make buildings better. And so this does not make buildings better. It creates the uncontrolled draft. These things, because they're hybrid, which means they can be electric resistance or heat pump. So they're going to work in an apartment when somebody switches them to their electric resistance mode. That's when you're going to get rid of the cold draft if you use hot water. Not everybody uses hot water. Sorry, I already told that joke. Go ahead.
It makes me worried you keep coming back to it. No. I'm curious if you can speak to it as a full year annualized COP, because obviously I think winter is a worst case in a lot of ways, but in summer the story's a bit different. And so, I mean, obviously there's higher delta T in winter, but it's largely helping in the summer. So I'm curious if these are annualized or not.
Yeah, so thank you for that. So in the summer, your apartment temperature is not that much different. You know, most people are comfortable at 75 to 80. In the winter, most people are comfortable at 70. So the delta T is not that different. In the summer, what we were interested in, and the unabridged version has this, is what we learned by looking at load calcs was that in the summer, the water heater, if we used a normal amount of hot water, would still cover the peak cooling load about 70% of the time. So when you have a decent cooling load, it's only 30% of the summer, not of the year, of the summer. So the water heater in a one-bedroom apartment was covering 2/3 of the peak load, which means that 70% of the time, roughly, you're going to have more heat, more cooling and humidity than dehumidification than you need. So you're still going to have a cold draft even in the summer. So the performance annually around the horn, if you will, is going to be better than the summer because you have more moisture and temperature in your incoming airstream, but not much. And your overall system efficiency is going to be worse in the winter because you're having to definitely replace that heat that's extracted by the water heater, and you don't definitely have to do that in the winter. And then there's other things like human comfort is a lot about, we hear it all winter long, wind chills. So we have this wind chill effect inside your apartment that's going to require a higher temperature in order for you to achieve the same comfort. because temperature is only one thing that dictates temperature. Humidity does, and air movement does as well. So time check. So we got to move here a little bit, but questions are great. So we are designing a lot of central plant air source heat pumps. And the reason why this is a title that's not an easy nut to crack, and this came up at our board meeting before this presentation, is that the cost of central air source heat pumps is high. It's 4 times that of a central gas-fired plant. And we have enough data to feel pretty confident about that. It takes more room. Something that I don't like is it's in multifamily, we want to be making systems simpler all the time if we expect good results in terms of operation. This is more of a commercial industrial solution, so it doesn't really fit well in a multifamily environment. And the operating cost is a problem because of that delta between the cost of gas and electricity. So we're doing a lot of work as an alternative to gas and not getting much benefit. So we're designing these commonly, and we've been since fall of 2022. They also, and Christina has experience with this, there's a swing tank involved in the Mitsubishi entry, and we have outcomes where the swing tank, which is supposed to be there to heat the recirc line, turns out to be heating the water. And any swing tank heating is electric resistance, and so that's a guaranteed COP of 1. So there's some problems associated with this approach. And there's an image. The outdoor units look a lot like heat and cooling. Outdoor VRF units, they're basically the same thing. And then we're getting a glimpse of a swing tank on the right and storage on the left. So we have more storage because it's a low recovery system. It doesn't heat water very fast, so we have to store more water using water as a battery. And we don't have to do that with gas because we get high recovery for low dollars. So we had a project where we talked about three different options for domestic hot water heating in a 625 bed new passive house dorm at Brandeis University, which is in construction. We ended up with an air source heat pump central, and then later on I had some aha moments and I said, boy, what if we use drain water heat recovery and solar pre-tempering, which is the option in the middle. And we'll say a little bit more about that. And then we also have ground source as an option. And it turns out all 3 of these had about the same COP. We figured that they're all about COP of 2. We could put in enough solar pre-tempering and enough drain water heat recovery, and then couple that or back that up with electric resistance and a lot of storage, and have a COP of 2 using old-fashioned technology. So I want to talk more about that. So solar thermal plus drain water heat recovery plus electric resistant storage option. So drain water heat recovery is a beautiful thing as far as I'm concerned. Did I just do a little Donald Trump? I'm sorry. I apologize. It's fantastic. So no compressors. It's just you're buying copper. The copper's in contact. There's again no compressor. Sometimes when I say drain water heat recovery, people say, oh, they went online, did some research, and then they come back. Do you mean this? And they show me a compressor-based system that extracts heat from your sewage. I don't like that. And it's got a COP of infinity and beyond. That was another, yeah. Okay, infinity, which is remarkable. So we're talking about COP of 4 being good, great. COP of 3 being like, wow, if you can. COP of 2 being more realistic. Infinity. Basically, to recover heat from the drain, we're not expending any more work. We're basically reusing the work we already did. I love it. And it should be cost competitive. It's unfamiliar to a lot of people. That makes it not popular. We tried to introduce it on the Brandeis project, too late. They already committed to a guaranteed maximum price. there wasn't much interest in it. This is what it looks like. One type, just a lot of copper. The makeup water's coming around the pipe, the water's going down the pipe. So we're replacing a section of PVC typically with copper, and it's pretty straightforward. This is the heat exchange performance is remarkably good. So when you're talking about heat exchangers, you often talk about the approach. The approach is the temperature between how much you're heating the incoming water, which is the bottom blue line, to the green line, and the difference between the green line and how much heat you're extracting from the drain water coming down, the shower water. So if we're going down the drain at about 100, which is what the temperature is, once it's taken some heat out of your body and it's evaporated a little bit, which cools it, so we're at 100 by the time we go down the drain, we get a pretty close approach, which really caught my eye, and that's why I'm showing this graphic. And we're recovering about 47% of the energy that we had to add to the water, which I think is remarkable. Anytime you're talking about percentage improvements that are more than 10, you should probably take it seriously. And here's what it looks like. You can have a stack of showers. You can also, in a single family home, you can make this work well. Something in here that you should scratch your head about if you haven't looked at this before is you're making up water to the cold side of the shower head and you're replacing water in the tank, and that way you have equal flow. Same amount of flow on the drain side as you have on the makeup water side, and that gives you the best heat recovery. This is another approach, same idea though, and we have an install in Massachusetts where we're taking the sewer where it exits the building and we're diverting it through copper and recovering heat. So in this case, we're not getting as much energy recovery because all the water is mixed together, cold, hot, everything. We're not having the water come up at the same time it's going down. There's a few factors that are cutting into our efficiency, but we're still getting 25%. And in measurements on our first installation, the manufacturer says we're getting closer to 30. So it's impressive. So 25% savings. This is a graph of data collection for, let's call it a whole building drain water heat recovery heat exchanger. Solar thermal, no compressors. Yeah, in the back. Emily.
Do you have any examples of that in multifamily affordable yet, or not?
Yeah, the installation in Massachusetts is a multifamily retrofit. Yeah, and we're looking forward to having more. If people would let us do it, we would have more installs. So we'd love your support in applying those two technologies. Christina, in the back.
Does it work with any of the best hot water systems that we just talked about? Like, would you only use it if you have a central heat pump water heater or a gas? Like, could you do it if you have a gas boiler or indirects? Like, what's the compatibility?
It works.
Will you paraphrase the question?
Yeah, sure. Thank you.
The audience
The
can-
first question was, do we have any multifamily in Massachusetts? And the answer is the one that I mentioned is the one, and it's in multifamily. And the second question, is it compatible with the different methods? Central, say, by apartment? Yes, but it's a little tricky. What we're doing is we're bringing the cold water service with the whole building approach. We're bringing the entire cold water service through that heat exchanger. And so what you're doing is you might, if you went to the faucet thinking, I'm in an ice cold 38 degrees, it might be 50 in the winter. And if you're thinking you're going to have some ice, in the summer you're going to get a lot of ice because instead of being 75, it might be 84 or something like that. So we're boosting the incoming cold water temperature year-round for the entire building.
Do people complain about that?
Only if they knew ahead of time that that's what was happening. Yeah.
And in the first case, do you have a dedicated sewer line for greywater as opposed to sewage? I said in the first case, do you have a dedicated drain system for the showers as opposed to
No,
the sewage?
we're just taking the building sewer exit. Just the one building, the building sewage that's leaving the building.
And you said in one case it's 44% and the other was 20 to 30?
When
What's the difference?
we have the copper in a stack,
Oh,
serving bathroom groups is going to be 44%, and we're going to need multiple of those in a building. And then if we're only getting the main sewer, we have just one of those in the building. And usually that takes less space, costs less, easier to retrofit. So it might be desirable.
Cool.
Yeah, back to you, Christina. Quick though, huh? Come on, this is number 2.
Real quick about
I'm just
that,
kidding.
too. I've heard with the central heat pump water heater systems that they like to see cold water, and that's how you get the high COPs with the big delta T.
Yeah,
So if
yeah.
suddenly this makeup water is warmer, does that make the COP of the Mitsubishi or whoever's heat pump water heater system lower?
Yes, it does. But let me look at that a different way. If you're trying to jack the COP of your Mitsubishi equipment, and you have to look at it as a system. So if you're more efficient raising the water from 50, whatever, 75 to 107 than you are raising it from 38 to 107, you're still using more energy than if you got the high entering water temperature. So you can't look at it in isolation. So folks that want the highest delta T across the Mitsubishi unit, they're kind of missing the point. We're trying to use less overall energy. So other manufacturers don't have that limitation, and Mitsubishi's coming out with new equipment that doesn't have that limitation. So on these systems that we're installing now, we don't get hung up by that. We're losing some efficiency with a higher entering water temperature, but we have to look at the overall energy use for heating domestic hot water. So this is a graph that I love. This is underneath the orange line is all the energy you need to heat the domestic hot water through an annual year. And it makes sense to you now, because I pointed out that the entering water temperature is cold in the winter, and it's warm in the summer. So that explains the graph, right? A lot of energy, twice as much as in the summer. Now the yellow bottom is us being smart about sizing the solar collector that's no bigger than it needs to be, but we want to cover all the domestic hot water heating in the summer when it's the sunniest, and then we get what we get in the shoulder seasons. So that's what this is illustrating. So this is how we'd size a solar thermal system to cut into that water that we have to raise. I think of the domestic hot water, the analogy is we improve the enclosure and dramatically reduce the amount of heating and cooling, and that's the key there. In domestic hot water, the analogous situation is we reduce the delta T that we have to raise the water. That's like making a good enclosure. So we're reducing the load and then addressing the remaining load. Brilliant, right? Go ahead.
I've seen math that shows that the system on the last slide is actually less cost effective than doing, that this system might be less cost effective than doing a solar electric, basically tied to an electric resistance element, and then in that case you can still net meter, for instance, if you were oversized for a moment.
Yeah, there was a really popular argument 10 or 15 years ago, and solar thermal absolutely got crushed because the incentives were geared for PV. There were all sorts of things that made it make more sense to do PV. One thing that I was surprised to find out is the amount of energy you can generate from a square foot of solar thermal is a lot more than PV. And that's why we're minimizing the size of the array, because we don't want to lose too much space. We don't want to lose too much space for PV. So we're optimizing the solar array by making it as small as possible and having it do as much work as possible. And the amount of work it's doing is a lot more than the PV. If they were equal in all respects in terms of energy generation, we're going to generate more energy with the solar thermal than we will with the PV. But there's other things. It's not that simple. Thank you for asking that. So I'm trying to represent the simplicity of solar thermal. You have a tank and you do as much work in the preheat tank, and sometimes you do all the work. And then the second tank becomes kind of storage, your main second tank. And then you also use a gravity drain back, keep it really simple. The controls for these are off the shelf. They've dumbed them down, more reliable. There are a lot of abandoned solar thermal that it never worked, that were installed in the 60s and 70s. We need to get around that. But again, it's all relative. So now that we're electrifying domestic hot water, solar thermal all of a sudden looks really good. And one way it looks really good is it all of a sudden is simpler than a compressor-based industrial commercial system. So everything is relative. So revisiting solar thermal is what I'm recommending. So the last part here, domestic hot water plant sizing. Just like with heating and cooling equipment, when you improve the enclosure, you have this remarkable opportunity to downsize heating and cooling way smaller than industry standard, way outside of the standard of care is another way of putting it. So you have certain square feet that a ton can cover of air conditioning, that gets blown away. So same with domestic hot water, but the big breakthrough in domestic hot water is that, again, with electrification, which is expensive to do and expensive to operate, we have to take a fresh look at what we're doing. And what we were doing when we were sizing gas-fired plants is we were way oversizing because there was no cost, literally, no dollar cost to speak of by oversizing them because the equipment was so inexpensive. Also, we weren't buying storage, so we were just buying boilers, and the boilers got more compact and more potent, if you will. The amount of BTUs they could generate got better and better over time, and the cost came down. So there wasn't a cost penalty to speak of to pay. And we were also using, we being HVAC and domestic hot water heating engineers, we were also using old references to say this is how much domestic hot water people use. So now what we're advocating is that we measure how much is actually used. So I'm going to just share a couple really quick case studies. Okay, so we weren't able to get the cooperation from owners to spend money to measure how much water they were using. But now, with electrification, we are. And that's been refreshing. So this is Old Colony, which is in its last phase. And so what we were able to do is actually measure flow on a prior phase. This was done in probably 8 or 9 phases since 2009 through the present. And so we were able to go to a previous phase and see how much water was actually being used. And there's 2 things we want to understand. We want to understand gallons per day per person. So if you have a storage system where you're collecting solar, you want to store hot water when the sun's out, and then you use it through a 24-hour period. And so what we really want to focus on in a high storage, low recovery system is the gallons per day per person. And they're remarkably low. So in this case, we're at 12.7 gallons per day per person. And just for context, an engineer who thought they were being accurate would assume 20 gallons per person per day. So we're at 12.7. The other thing we want to understand is the peak. What's the worst case? We need to have enough hot water for when the most people are showering. So that's what we're measuring here, and we measure that in gallons per minute. That's the peak. So if we have an instantaneous water heater with no storage, which is high recovery, 0 storage, it has to be able to meet that peak. So we want to know those 2 data points. So here's an existing dorm. This is at my alma mater, the University of New Hampshire. Best hockey team to never win the national championship. Okay, so this is the largest dorm on campus. They had these gas water heaters with a large storage tank behind it. And it was in disrepair. It had to be changed, and it had to be changed quick. And they had a tight budget, of course. New Hampshire doesn't do a good job of supporting its higher ed. So these are the conditions. They were okay with natural gas. They had good luck previously with instantaneous water heaters, so we used all that. And so we measured. So they understood the benefit of measuring. And so here's a GPM in a freshman college dorm, which is fascinating in and of itself. So this is a sample day, and the peak GPM is about 6 GPM. This is 600 beds.
600 beds.
600 bed dorm. Peak GPM is 6. Here's another day. One's a weekday, one's a weekend.
Wait, not 600, just
6. 6 peak GPM. Yeah, these are hard to believe. Here's 12. here's 12, and then I think this is on a Saturday, and that's at 9:30 a.m. Yeah, I know, I had the same reaction. Here's gallons per day, if that didn't blow you away. 2 gallons per day per bed. No, this is worse than in the summer. This is in September when nobody's been sent home yet for misconduct. This is the absolute busiest time of the year. 2.
That's absurd.
Yeah, so we had 2 GPD and 12 GPM, and the code prescribed, international plumbing code, which does not apply in Massachusetts. It has its own code. But using guidance from the International Plumbing Code, we would have designed for 21 gallons per day per person and 57 GPM. I know. Don't worry, we didn't design to that because the owner said, I'm not quite ready for 2 and 12. So we ended up with like 28. We did an N+1, which is we had one instantaneous boiler that could cover the whole load, and then we just had a second boiler just in case. And he said, let's see next time. We have not had one complaint with the installation. It's been in probably a year. And then this is the Brandeis University, which is in construction right now. It's a really great project. I think it's 625 beds, passive house. That's a floor plan. In this case, this is 630 beds. In this case, we had a neighboring project that was completed 5 years prior, not as many beds. And this is the weird thing, University of New Hampshire, there's different behavior. I don't know if it's public-private, I don't know. But these students use more, but not much. So this is a peak GPM that for some reason got worse on consecutive days. I can't explain that. Is this a Brandeis University grad that wants another question?
I'm curious. So I mean, our company does a lot of like single-family hot water heaters, and we see a lot of data that is higher than this for a single house.
Sure.
Or at least comparable. Is this because there are no bathtubs and like very strict shower head requirements, and there's different shower heads between campuses or something? Like, I'm curious how deep you went on it.
Well, I can't go that deep because I can't pry into the lives of undergrads.
Or is this the junior dorm and they learned this in those 2 years?
Everybody in this room has just as much expertise as I do on this. I'm just telling you what the data is. You can all decide what it means. But we are designing to it. Gallons per day per person. Brandeis, is this being recorded?
Yes.
Brandeis is using 3 times as much hot water as the University of New Hampshire. Sorry, UNH. Anyway, so we do end up designing to that data, and that's probably the biggest lever mover is not oversizing. So I'm going to end there. Thank you, everybody.
Thank you so much, James. Maybe we should be praising them for being efficient. Maybe they're just committed to efficiency up in New Hampshire.
I think they're not home. That's my leading theory. They're not in their rooms.
In person,
they're in the library.
Some questions. So we'll take one from the chat first, and then we'll go to in person. First question comes from Passive House, Massachusetts board member Lauren Bauman. Is the 4x cost increase for central heat pump systems related to swing tank efficiency being blended, assuming the spark rate is right around 4?
Let me just clarify. So it's first cost. So the all-in first cost for the plant is 4 times. And we don't get a lot of good pricing information. So we have a sample group of 2, which is pretty good. It's better than 0. And that's in both, we're in pretty rough agreement that the cost, and this is just for the mechanical equipment, not for the size of the room or anything like that. The mechanical equipment is 4 times more for a central air source heat pump, Mitsubishi or otherwise, than it is for a central gas.
Also note that the clipboard that's going around, if you haven't already signed in, we want to make sure you sign in so we know that you came, and also that you use. A question from the audience before we go back to the chat?
Hi, Matthew Colesbury, SGH. 2 questions. First, on the hybrid heat pump water heaters, making sure I'm understanding correctly, it's both an energy consumption problem overall and a comfort problem, or just one of them? My second question was on the drain heat recovery devices, asking for our support to get them implemented more. Is it cost prohibitive? Is it lack of familiarity, limited products? What's the barriers as to why we're not seeing it? Or labor intensive to install, hard to find the space to find a good location to put it? Just why is it not as common if it's so obviously beneficial?
I'll start with the last one, and then you'll have to remind me of the first one. And we ran into this when we first started applying air source heat pump technology in buildings, is we were out alone doing that, and it was brutal. So familiarity. So we have only recently been promoting this. It was kind of an aha that we should revisit solar thermal and incorporate drain water. We've used both. For example, drain water heat recovery, we used it at YWCA, probably 20 years ago, where you have a lot of showering, obviously, and it flew there. But that was our only application. So there's also not sex appeal. You know, there's no heat pump in the word. And there's something about heat pumps, and that's dogged me for 40 years. Because back 40 years ago, heat pumps just had this mystique about them, and these were water source heat pumps with a cooling tower and central boiler, and they were very common in offices and other commercial buildings. But there was just something about it, and I could put a label on each reason why in each decade there was something appealing about heat pumps, but there's not that same sex appeal with just a hunk of copper, although I think copper's amazing.
Add the word free.
Pardon me?
Add the word free.
Free. Yeah, I have to come, you know, I would think COP Infinity would be pretty sexy.
That's pretty good.
And then, so I think that also, you know, it's hard for people to kind of, and I hope people latch onto it. People have to get excited about it, they have to understand it. You know, I said that when people search it, what pops up is compressor-based wastewater heat pump. And so we have to, there's the availability of it is limited. There's a manufacturer in Canada, that the person that we're working with. So there could be more manufacturing. He's done a lot to keep price. Copper does this, it's a commodity. He's done a lot to keep that steady. So he's done a lot of good work to make this available. And so I'm hoping I hope it takes off just through the same way other things have come around for us, is we just have to stay on it, beat the drum, educate ourselves and others. So that's what I'm hoping for with that. Quick on the first question. So yes, it's both. The problems are completely separate, and they're both problems. And I think the number one, the most important problem is occupant comfort. So the cold draft is number one for me. We can't be incentivizing this because they're not making buildings better. The other thing that we're having, and this came up in our board meeting, is there was a conversation not about domestic, it was inspired by domestic hot water, is the co-requisite programs in FIAS, not in PHI, they don't have co-requisite programs, but the co-requisite questions are getting it wrong. So if we have electric resistance in a market rate project, we can't use it now because, well, we can use it, but the pathways for compliance through the co-requisites are being eliminated. So they have a required efficiency for water heaters in one of the pathways. It used to be 1, so we were okay with electric resistance. Now it's 1.5 or 6 per one of the pathways and 2. So it's basically saying this has to be a hybrid heat pump, and hybrid heat pumps in apartments are a bad idea. So that's comfort and the associated problems. And then the total efficiency isn't well understood. There's so many workarounds where people say, oh, put it behind the fridge. Why can't you exhaust it outdoors? Refrigerators don't generate a lot of heat unless you leave the doors open, the freezer and the refrigerator. Even then, they're not going to generate a lot of heat because you're basically extracting heat from the room. That doesn't work. And so, and we even, when we were really digging in on this, probably 3 or 4 years ago in our office, an engineer in my office actually ended up with the inventor of the hybrid heat pump on the phone. And he said, these are not a fit for apartments. So his understanding of where these applies was the same as ours. And that was reinforcement that was valuable for us. That we knew we were on the right track with the cold draft. All we had to do was do the math.
Two quick questions from online. From Walter Sharp, what is the COP for ground source heat pump with water to water for domestic hot water purposes? And then from Kurt Lamar, do these hot water heat pump systems freeze up in super cold temperatures? And do they have a defrost mode that might rectify this?
Okay. The second one, I can't answer yet, but the first one is ground source heat pump. When you're comparing to infinity and over 200, which is solar thermal, because in solar thermal all you're doing is running a small pump. I know that ground source heat pump, with confidence, we know it's less than 10. We also know it's less than 5. Anytime you turn on a compressor, you're restricted to less than 5. So now you're talking about, now you can argue, and I don't really care what the argument, I do. Is it 2? Is it 3? Is it 4? Maybe it's 4, probably not, but it's not dramatic. Ground source heat pumps are not dramatically more efficient overall. They have different ambient conditions. It's cold in the winter, hot in the summer. In the atmosphere, it's relatively stable, but there's still some fluctuation in the ground. There's not a dramatic efficiency delta between the two. There's a perception that ground source is wonderful. It's the most wonderful of all the heat pumps, of all the compressor-based systems. It's not that much better than air source. If you want to be really aggressive, call it 3.5, but plan on 3. And I could do a little bit more work to narrow that in a little further. So I don't have great math on that right now. The other question was defrost. I assume we're talking about a central heat pump because we are using an outside unit. So we're exposed to the same harsh environment as heating with an outsource compressor-based system. We have the same conditions. We're trying to extract heat from a increasingly hostile environment as the outdoor temperature goes down. We can do it, but it gets harder the lower the temperature is outdoors. That's inherently the case. So I don't think we have issues with frost or things of that nature. We also don't design backup. Some engineers design backup, but we don't. We're all in. We can put out an additional condensing unit. We can leave room for adding a condensing unit. We want to stay away from oversizing. The problem with electric resistance backup in the central plant is you end up using it accidentally. So that's why we try to prevent it from getting on the job. You can't use something you don't have.
Okay. One last question, and then I'll close it up.
I work primarily in Cambridge, where new gas lines aren't allowed. Are there ways to boost the efficiency of some of these heat pump versions or electric versions to make it better for multi-family housing, even when gas isn't an option at all?
Yeah, and we've covered a bunch of those. I'm going to recap. We want to eliminate the amount of temperature. This is a good closing question. We want to eliminate the amount of work we have to do. And so if we can increase the incoming water temperature, we want to do that. We want to do that using solar, thermal, and drain water. And then we want to address the remainder. It's not always about using the least amount of energy, and that's why I'm getting into, that's why I'm suggesting, why not invest in a really big storage tank with electric resistance that just chugs away and makes hot water when it has to, when you don't have enough solar thermal and you don't have enough drain water help. You get drain water help year-round, by the way. You only get solar when the sun's out. So there's going to be times when you need a little boost. I'm suggesting you spend money on solar thermal and drain water. Don't spend money on the air source heat pump technology. It's really expensive. Buy a really low-cost electric resistance and invest some money in a really nice big storage tank. Figure out a way to do that. That's what I'm suggesting as what I would like to see. If I had if it was my 100-unit multifamily, that's what I'd be putting in as a system. If you had money because your relative just passed away, you could do the solar thermal, the drain water, and then air source heat pump. But it just seems like too much investment, too much risk, just too much. Yeah.
Better to use that money on a donation or a membership. Thank you. Let's have a big round of applause for James Petersen.
Thanks, everyone.